Okay, Happy New Year. Welcome back, literature fans. Today we'll do still another variation on the Johnson-Jackson Pythagorean Theorem proof. And of course, as you know, Johnson and Jackson do things more trigonometry. I use more of an area approach, namely this A1, big one, consists of A2 and A3. Here's A1, here's A2, A3. A2 is the one that we need to calculate. In my previous videos, I got A2, well, using base times height times 1/2. That's one approach. The other second approach was to get the sum of these individual similar triangles, an infinite number of them. That's a geometric series. And again, A2 basically has to add up to this 2a squared b over b squared minus a squared, which is right here. A1, that's 1/2 of this u, which we calculated before, times c. And A3 is simply 1/2 of 2a times b. So the most challenging is this A2 that we're calculating. So we'll use two variations. One is the cross product, and the other one is Meister's formula. Cross product is basically you have a distance m times n times sine theta of this theta, and of course 1/2 because this is a triangle. Otherwise you would be getting the area of this parallelogram. But we want only this one, so 1/2. That's what we need. In Meister's formula, that one is very useful if you have the exact coordinates x1, y1, and x2, y2. So we have 2 points. And this is a cross product. Well, it's a determinant. It's 1/2 of a determinant, x1, y2 minus x2, y1. And so using this first approach, this cross product, mn sine theta, that A2 would be, well, it's 1/2 2a times this u, which we already figured out previously in the previous video. Here it is. And times the sine of alpha, right? Sine of alpha is a over c. So you see all these components here. And then when you do the simplification, then it all cancels out nicely, and you get 2a3 b over b squared minus a squared, which is over here, which plugs in nicely here. When you add it all up, cancel things out, you get a squared plus b squared equals c squared. So that's one way. So using Meister's formula, we have to get these coordinates x1, y1, and x2, y2, and everything is referenced to our 0. This is our starting point. Origin is here, and so you can see the value of y1 will be negative in this coordinate system because we are below we're going negative this way, positive this way on the y values, and positive x, negative x this way. And so the value of x1, if you add up all of these little values, well, it is 2a times this bracketed thing, 1 plus a squared over b squared plus a fourth over b fourth, a6 over b6 plus dot 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 infinite process, limiting process, which is the same thing as here. That's 1 over 1 minus a squared minus over b squared, the whole thing times 2a. Simplify that, you get 2ab squared over b squared minus a squared. Okay, so using Meister's formula, the value for y1 is essentially you factor out this 2a squared over b out of each of these heights, and you get a similar type of progression here, series. So you got 2a squared over b times this series here, which we saw before, and that's basically this. Going from here to here is a limiting process. Simplify this, you get this, and then going further you get 2a squared b over b squared minus a squared. However, remember, this is now, sign is important. Here's 0. This is negative, so we have to have a negative sign because we are in this coordinate system now, and negative values matter. So it is negative because this is a 0, 0. So the x value positive, but the y value negative. So 2a squared b over b squared minus a squared. So let's put it together. We had our x1 is equal to 2ab squared over b squared minus a squared, and y1 is negative. Don't forget the negative. 2a squared b over b squared minus a squared. So here's Meister's formula. Here's the 1/2 of the determinant, which is x1, and y2 is 0. So this actually just goes to nothing. And then minus 2a, that's x2, and then y1, it's this negative 2a squared b over b squared minus a squared, and the negative cancels out the negative, and so when you simplify, it's 2a third b over b squared minus a squared, which that's the same thing as over here. This is what we need to plug in here. When you plug it all together, just like we did with previous videos, a1 equals a2 plus a3, things cancel out, and you get c squared equals a squared minus b squared. Pretty simple. So you can see the different approaches here. Essentially, here we had the cross product, mn times sine theta over 2, and Meister's formula, that's a determinant, and it's x1 y2 minus x2 y1, the whole thing over 1/2 because it is a triangle. Okay, so if you have exact values of x1, y2, x2, y1, you can calculate the area exactly using rational numbers. That's not the same case if you use this cross product, mn sine theta. Anytime you take a sine of some angle, you will probably not get an exact answer. So this is an approximate answer. This is beautiful. This gives you exact rational value for area. That is awesome. Love it. Anyway, so an area-based approach to the Johnson-Jackson Pythagorean Theorem proof.